So it's finally time for me to get out this video about this giant, ridiculous, massive beast of a graphics card from 1998. This is a high-end professional workstation card from 3D Labs called the GMX 2000. I had originally intended for this to be a GPU June video, and I also wanted to run a lot of benchmarks for this video, but kind of waited too long, and it was getting down to the end, and I started recording things and running the benchmarks, and then I looked at how long they were taking to run, and I quickly did some math, and I realized there is physically not enough time left to run all these benchmarks and get this done before it's July. So I decided to run a bunch more benchmarks. So this was originally going to be a test of this card versus one other card, and now it's going to be this card versus two other cards. So there's a lot of stuff, and this is probably going to be a pretty long video, so I'm not going to mess around, and let's just jump right on in. Let's talk a little bit about this card and what makes it interesting. There's a lot going on here. There are 4 major chips with heat sinks or fans. There's an ocean of memory chips on both sides. Under the very small fan is the Glint Gamma. Among other things, this chip acts as a PCI bridge to access all of the other chips on the card. I'll come back to this chip in a bit, but I'll mention that this fan is one of the most annoying things about this card because it is so small. It has to run at about 1 billion RPM, and it gives off a loud, high-pitched sound that just about drove me nuts while running all the benchmarks for this video. The chip with just a heatsink on it is a Promedia 2V. This chip handles DOS and Windows 95, Windows 98 compatibility. Display output in Windows NT and Windows 2000 is handled by this TI chip. This is another annoying thing about this card. There are no Windows 95 or Windows 98 drivers for the real hardware. All you get is a 2 megabyte, because there's this RAM chip and another on the back, a 2 megabyte Promedia 2. Under the 2 larger, nearly silent fans are the Glint MX chips. These are the rasterizer chips, and this particular card is a dual rasterizer. If memory serves me properly, these operate in something like an SLI kind of configuration. Now, there were other cards similar to this, like the Elsa Gloria XXL that had only a single MX rasterizer. Now, each of these rasterizers has its own dedicated memory. That's all of this EDO RAM that's on both sides. And this memory is for local render targets and for texture memory. So each chip has a whopping 32 megabytes, which, considering that the Riva TNT from around the same time has 16 megabytes total for everything, that's a massive amount of RAM. With the render targets carved off from the MX memory, that gives an effective about 25 megabytes of total texture memory. Now, all textures have to be duplicated in both memory pools so that each chip can access it, which is why out of 64 megabytes, it's, effectively 32 megabytes with a chunk cut off. Now, the Gamma. In addition to acting as a PCI bridge, the Gamma performs triangle setup to feed the 2 MX chips. And if that wasn't enough, it performs full OpenGL 1.1 hardware TNL. it has an additional 32 megabytes of RAM, where it stores frame buffer, vertex data, and command buffers. Now, vertex data is a little bit of a misnomer. Now, all PC gaming cards, starting with the original Radeon and the original GeForce, store vertex data as just large blocks of floating point data. And the hardware rendering commands basically say, at this address with this layout, here's 1,000 triangles worth of data, go. But workstation cards don't generally work that way. Cards like this and pretty much all SGI graphics hardware and some others want to operate on lists of commands that set vertex position or texture or color values in hardware registers. And this kind of hardware really wants to be fed by OpenGL display lists. So in reality, the VRAM attached to the Gamma is filled with lists of commands that write to these hardware registers. This had some advantage when, say, all of the triangles in a group of triangles had the same color. Color only needed to be set once instead of once per vertex. It was also very common for some attributes like specular color, which was usually white, to be set once per model or once per scene even. So the display list only needed to store a single command instead of hundreds or thousands of copies of the same per vertex value. There's an interesting presentation about the Gamma and the MX that was shown at some conferences around the time these chips were released. In addition to the hardware architecture details in the presentation, there's some interesting commentary about 3D graphics in general. Not all of this commentary has aged very well. My favorite is 3D geometry is well understood. Don't need the luxury of programmability. The majority of my day job for the last 10 years or more has been working on a compiler for programmable GPUs. The other funny thing about this presentation is that it was given by a man named Neil Trevette. At the time, he was VP of Marketing at 3D Labs. These days, he's VP of Developer Ecosystems at NVIDIA. He's also the president of the Khronos Group. Khronos is the standards body that controls OpenGL, OpenCL, Vulkan, and a bunch of other graphics and GPU-related API standards. So in that capacity, Neil and I have worked together for more than 15 years. So it was funny to see his name on a slide deck from long before I knew him. Now, 3D Labs had another older chip that could also feed an MX, the Glint Delta. Now, they build the Delta as a geometry processor, but all it did was triangle scan conversion. That's the process of interpolating between the vertices of a triangle to determine what the values for texture coordinates and colors should be at the ends of each horizontal line that's covered by the triangle. The the Elsa Gloria XL used a Delta to feed an MX. This is a much, much older card. The Gamma is fully register compatible with the Delta, so it can operate in that same mode, and I expect that was really helpful in doing early driver bring up for this card, because then you didn't really need to program the Gamma. You could just treat it as a Delta, and you only had to worry about the new things about these chips instead of having to bring up all of everything at once. Now, interestingly, the Promedia 2 on this card and on several other Gamma MX cards has a fully register compatible implementation of the Delta on die. The successor to the MX, the Glint R3, also has a Delta on die. The Glint R3 is also known as the Permedia 3. So this VX1, which is probably really nearly impossible to read, this VX1 card and another VX1 card that I have will return in a video highlighting another piece of truly weird stuff. But I'm trying to get a couple of other components together for that video first. And that may take a while. A couple of these things I've been trying to track down for years. So I'm not holding my breath. And I recommend you don't also. Now, this split between scan conversion and rasterization isn't too terribly different from what 3DFX did with the Voodoo and Voodoo 2. The main difference was in 3DFX's case, much more of the work of rasterization was done on the chip that did triangle scan conversion, and the other chip or chips, depending on which card and what configuration we're talking about, focused pretty much exclusively on texture mapping. And I think that really reflects the differing performance emphasis between the workstation and gaming markets in the mid-late 90s. Now that is kind of a nice segue to the performance testing that I did on this card. So this particular card was released in 1998. So I've picked 1998 appropriate hardware and software to go with it. And since it's a very high-end card, I want to say when it was released in 1998, it cost about $2,000. It's high-end software and hardware. Ish. For software, I'm using Windows NT 4.0 Service Pack 6. The installation of the GMX 2000 drivers on NT4 was super easy. I was able to download the latest drivers for NT 4.0 from the 3D Labs website. That's no joke. They still have drivers posted for many ancient cards and ancient operating systems. It's like they forgot to have someone go in there and just delete all that old crap. For benchmarking, because you know there's going to be benchmarking, I'll be using Quake 2 version 3.20. Quake 2 came out in late 1997, so it's a good game to try to run on 1998 hardware. I'm going to use the Massive1 and the Crusher time demos. There's links to all this stuff in the description below. I'm also testing with SPECviewperf 7.1. Viewperf is basically a collection of recordings of OpenGL calls made by a handful of workstation applications like 3D Studio Max and CATIA and a bunch of high-end things like that. This is the oldest version that I could find, 7.1, and it was released in 2003, which is 5 years after the GMX 2000 was released. I don't expect any 1998 cards to perform well on that test. But what makes it interesting is back in the early 2000s kind of time frame, I know we had a lot of trouble in the Mesa open source drivers getting Viewperf to run without crashing. So the issue with those kinds of applications that Viewperf represents is they push a huge pile of data at the driver, and that caused problems. The big problem for the drivers in Mesa were that some of the hardware that we were talking about could only process so many triangles at a time. And so if a single draw call had more triangles than the hardware could handle at once, the driver has to split the draw call. And in some cases for for some kinds of OpenGL drawing modes, that can be really hard to do correctly. So it'll be interesting to see if the drivers for the various cards that I'm going to test are up to the task. For hardware, I have a fully maxed out Tiger 100 motherboard with a gigabyte of SD RAM. I don't even want to think about how much a gigabyte of RAM would have cost in 1998. But if you're spending $2,000 on a video card, you know, you can afford it. I used a variety of CPU configurations. The best 1998 configuration that I could test was dual 400 megahertz Pentium 2s. The 450 was also available in 1998, but I don't have any, so I couldn't test that. I also tested a couple single and dual processor Pentium 3 configurations, even though the Pentium 3 wouldn't come out until early 1999. For direct competition, let me dig back through my pile here, I'm going to test against the Riva TNT, which was the best single card solution for gaming in 1998. I do have a pair of 12 megabyte Voodoo 2 cards that I could test. I chose to not even bother for a couple of reasons. One, I completely ran out of time for this project. And two, the Voodoo 2 drivers for both Windows NT and even Windows 2000 were just terrible. So if I can't run the GMX on Windows 98, I don't want to run Voodoo 2s on Windows 98 either. So there wasn't really a useful comparison to be made there. Now, the VX1, like I mentioned before, came out in 1999, but I'm going to test it too. My expectation is that it will do better at Quake 2, even though it's a single rasterizer card, but worse, probably much worse at ViewPerf due to the lack of a geometry processor. Would really like to have a GVX1 or GVX2 card. Those pair a gamma with either 1 or 2 Glint R3 chips, respectively. At some point, I'm going to start a series called Computer of the Year, where I will highlight the if money were no object computer for a particular year. Now, these years will coincide with the release of some interesting piece of software. So 1998 will come back around. There was some interesting software in 1998. But spoiler alert, it'll probably be without the GMX 2000 and will probably be with the Riva TNT. So let's now go ahead and transition over and look at some of the benchmark results. For all of the benchmarks, the desktop was set to 24-bit color at 1280 by 1024. That resolution was chosen because several of the ViewPerf benchmarks open a window of that size. As far as I can tell, the GMX 2000 can only do 24-bit color, so both other cards were benchmarked at the same color depth in everything. In Quake 2, I started with the Massive1 benchmark. On the GMX, Quake 2 really isn't playable at any resolution with any CPU that I have. I ran a bunch of reasonable resolutions that someone may have wanted to use in 1998 or 1999, and also 1600 by 1200 just for giggles. I feel like seeing Quake 2 run at all at 1200 or at 1600 by 1200 in 1998, even at 6 frames per second, would have been pretty impressive. The only reason this card was able to do this is the huge amount of memory that it has. The card is actually capable of 4 full 1080p. I was too lazy to drag a monitor over that could do 1080p, but I suspect that this card would have run it properly at, 4 frames per second or something. The highest score in the Massive1 time demo was a very disappointing 26.4 frames per second. At the time, hardware reviews said that you needed at least 30 frames per second for competitive online play. And this card is only able to get somewhat close to that with a CPU that did not exist in 1998. My guess is the small amount of CPU scaling that happens across these benchmarks is due to the improved performance of the driver copying vertex data to the card every single frame. The way that Quake 2 uses the OpenGL API is not really ideal for either multi-threaded drivers or for hardware TNL, which are kind of similar cases. In the multi-threaded case where you have multiple CPUs, really the other CPU becomes your hardware TNL unit. There is a little bit of performance boost from using dual CPUs, but it's pretty small. So graphics drivers have 2 parts. One part runs in the same address space and the same sort of protection zone as the application. This is called the user mode driver, or the UMD. This part is responsible for converting API commands like draw a triangle or switch textures into lists of hardware commands. And this is a bit like a compiler that converts a high-level programming language into machine code. And then you have another part. So the UMD can't talk directly to the graphics hardware. That would be a security hole bigger than the Grand Canyon. Like, if any application could just poke at the hardware, it would be like Windows 3.1. Instead, the UMD submits the commands to a driver that runs inside the operating system kernel, and this is called the kernel mode driver, or KMD. So basically, really simplify here, the UMD asks the KMD, would you be so kind as to submit these commands to the hardware? And this is how it works on Windows and Linux and Mac OS and basically every operating system. So my guess is that the multiprocessor speed up that happens here is because the application and the UMD are running on one CPU while the KMD and the rest of the kernel are running on the other CPU. So this also implies that the KMD is doing a fair amount of work. By having these on separate CPUs, the UMD and the application don't have to wait for the KMD to finish its work before they can move on to the next thing. Now, this is all just speculation based on I've been doing driver development for a really long time, and that's what my guess is based on looking at this very small amount of data. I may be completely wrong. Now, the scores in Crusher are even worse than in Massive1, which is to be expected. That's perfectly normal. But Crusher topped out at just a horrifying 21.6 frames per second. So the reason this time demo is almost always slower is it has a lot more players on screen and a lot more particle effects happening all on screen. And there's a lot less just like bulk scene geometry that can be submitted. And as a result, it is a lot more demanding on the CPU. So I don't really have the best frame of reference for looking at ViewPerf scores. Especially this particular version of ViewPerf, which was the oldest one that I could find and is just really, really crushing on all of these cards. I mean, this version of ViewPerf didn't come out until, I think, before I said 2003. So 5 years after this card came out. So there was no way that it was gonna be a happy time. So one thing that I do find interesting in it is there's a lot of, there is a complete lack of CPU dependency in the scores. all of these applications make really heavy use of display lists, which is the ideal way to use either in these versions of OpenGL, which we're talking about OpenGL 1.1, is kind of the ideal way to use it on hardware that has either hardware TNL or multiple processors. So realistically, these benchmarks should run almost entirely on the graphics card. Most of what should be happening by the CPU is just submitting commands to swap what's on the card, because I don't think that that everything can fit in the on-card memory as massive as the on-card memory is. So switching to the VX1, I believe the VX1 and the GVX1 is the generation when 3D Labs first started advertising their multiprocessor optimized power threads driver. And I believe that they also claimed that this particular driver was very heavily optimized for SSE. So based on that, I would have expected the performance increase at 640 by 480 going from the 400 megahertz Pentium 2 to the 450 megahertz Pentium 3 to be larger. It's about the same in relative terms as the step from the 450 megahertz Pentium 3 to the 500 megahertz Pentium 3. And this is about the same. I mean, this is the same change in frequency, but the former adds SSE. So it seems like with that first 50 megahertz step that also added SSE, you should have gotten more out of it. The big jump that happens with the CPU scaling is with the 600 megahertz Coppermine Pentium 3. I am expecting that the change from half speed L2 cache to full speed L2 cache is responsible for that. So going from the earlier Pentium 3s, the L2 cache was in physically separate chips, and it ran at half the CPU speed. And starting with the Coppermine, the cache was moved on die and ran at full die speed. The boost from multiple processors is bigger here than it was on the GMX 2000. With the Power Threads driver, all of the TNL work that was done on the Gamma is now done on the second processor. Even so, if Quake 2 were using the GL API in a more ideal way for this kind of hardware configuration, the dual 500 megahertz system should have outperformed the 600 megahertz Coppermine by a pretty good margin. Now, all of these scores soundly beat the GMX 2000. The GMX 2000 has dual rasterizers, but the addition of multi-texture in the VX1 is such a huge advantage in these kind of games. The VX1 is going to come back in a future video, and when I bring it back, I'm going to see how it fares with multi-texture disabled in this application, and see how much of a hit it takes, and if that puts it more on a level with the GMX. I mean, there obviously were other architectural changes that happened across those generations. There was one other weird thing in Quake 2. When my benchmark scripts, because I scripted all of this once I remembered how to run all these benchmarks, because it had been a minute. When the scripts switched from 640 by 480 to 800 by 600 on this card, the resolution change did not happen gracefully. On the first run of either of the Quake 2 benchmarks, the screen would just be scrambled, and the performance was terrible. I mean, it took like a 20% performance hit. And looking at the screen, it looks like either the part of the display hardware that fetches from memory was set up for 800 by 600, but the thing that actually talks to the monitor was still set for 640 by 480, or vice versa. Anyway, it was very odd. It was 100% reproducible. It happened on every single run when it hit that, on every single CPU combination when it hit that transition. So it's too bad I can't submit a bug report to 3D Labs and see if they would see if they would fix this, 23-year-old bug or whatever. So in Crusher, the VX1 can't hit 30 frames per second at any resolution with any CPU. It feels like it's still CPU limited though. This motherboard can take a 850 megahertz Coppermine, a pair of 850 megahertz Coppermine CPUs. A fully maxed out system might be able to hit 30 FPS at 640 by 480. Now, like I mentioned before, the same kinds of 1998 OpenGL API usage that would have been good for hardware TNL is also good for multiprocessor optimized drivers. In SPECviewperf, this really starts to shine. The performance jump from a single processor to dual processors is just outstanding here. Even so, the dual 500 megahertz Pentium 3 on the VX1 could only beat the slowest score on the GMX 2000 in the 3D Studio Max test. It gets really close also in IBM's Visualization Data Explorer. It's a DX08 in the benchmark list. Everywhere else, the VX1 does not even come close to the GMX 2000. Another thing that's interesting is several of the benchmarks show a very large step going from the 400 megahertz Pentium 2 to the 450 megahertz Pentium 3. And this suggests that the SSE optimizations are finally paying off here. It's not really clear why Quake 2 doesn't show a similar speed up. I mean, perhaps there's just too little geometry needing TNL processing for it to matter. I don't know. But overall, these VX1 results are basically what I predicted. The VX1 is much better in cases where texture mapping performance matters, and the GMX 2000 is much better in cases where geometry processing matters. I'm curious to see how a GVX1, which adds the gamma geometry processor from the GMX 2000 to the VX1, would fare in a couple of these benchmarks. In some of them, the gap is large enough that I suspect it's possible the dual rasterizers on the GMX 2000 are helping out quite a bit. None of those tests are doing any texture mapping to speak of. There's a little bit in a couple of them. Most of it is just shaded polygons and lots of anti-aliased lines. So it is definitely possible that the dual rasterizers help out a lot there. And then we get to the TNT. Now, the TNT was unable to run at 1600 by 1200. At that resolution, the frame buffer and the rendering target buffer and the depth buffer use almost 15 megabytes. And this is a 16 megabyte card. So having roughly 1 megabyte left for textures and command buffers and everything else is not going to work. It may work a little bit better on Windows 98. Windows NT doesn't really support AGP, so the AGP slot is just a fast PCI slot. On Windows 98 that actually has AGP support, being able to do AGP texturing, it may have actually been able to run these benchmarks, but not here. I mean, it was so bad that when I first started with the TNT, after I had switched off of the last VX1 benchmark where Quake was remembering to run at 1600 by 1200, it just came up with a gray screen and sat there for a minute. And I'm not exaggerating. I thought, oh crap, these drivers don't work. I'm going to have to go find different drivers. And then it switched to another screen and sat there for like a minute. And I thought, well, wait, what's happening? and then I figured it out. And I had to use Control-Alt-Delete to get to Task Manager to just terminate the program. So while those scores are missing, the scores that are here tell quite a story. The TNT is very CPU dependent, and it beats the other cards almost universally with a couple outliers. The VX1 puts up a good fight at 640 by 480 with the 600 megahertz Coppermine CPU. The VX1 actually outperforms the TNT at 800 by 600 and 1024 by 768. And that really surprised me. We'll see if it can still hold up in the more CPU intensive Crusher demo. So in Crusher, the TNT just pulls even farther ahead. The CPU dependency of the VX1 really holds it back here. It's possible that fully maxed out dual 850 megahertz CPU configuration, maybe then the VX1 could outperform the TNT across the board. I mean, maybe. It's a fun thought experiment, and I will probably do that experiment eventually. But keep in mind, the VX1 came out a year after the TNT, and by that time, the TNT2 was out. The TNT was one of the first cards that really did 32-bit rendering for gaming, and it was optimized for 16-bit rendering. I mean, realistically, the TNT2 was much, much faster than the original TNT at 32-bit rendering, and I don't feel like any level of CPU megahertz are gonna make the VX1 catch up with a TNT2. Like, if you're gonna pick on my little brother, but I suppose anything is possible. Anyway, the TNT2 is definitely a lot more in the land of playability. At least with the higher CPU speeds at the lower resolutions than the VX1. Now, the thing that is interesting is there is zero performance difference between the single CPU configurations and the dual CPU configurations. So this suggests to me that the KMD for the TNT doesn't do very much at all. And so by having everyone run on basically one CPU, there's just no extra performance to be wrung out by switching, putting the kernel on its own CPU or anything like that. Now in ViewPerf, there's a totally different story. The TNT's ViewPerf scores are, frankly, pretty dire. The TNT outperforms the VX1 in design review, the DRV09 benchmark, at lower CPU speeds, but as the CPU speed picks up, the VX1 pulls out into the lead. The TN2 is also slightly ahead of the VX1 in Unigraphics, the UGS03 benchmark. Everywhere else, the VX1 is just ahead. It just leads. But, for a card that is a year newer, it feels like the gap should be bigger than it is. I mean, especially with this having come from a kind of workstation heritage. I don't know. It feels like the VX1 should have beat the TNT more soundly in ViewPerf. And, the TNT can't even touch the GMX 2000. Which, I mean, it seems like a $2,000 graphics card should be able to beat a $200 graphics card at something. So at least it gets a good solid win here. All right. Well, I guess that answers the question. I think we knew it was coming. No, that is not the best 1998 Windows NT Quake 2 card. That's a mouthful. Since I recorded the earlier part of the video where I was going on about how great it was that I could just download drivers from 3D Lab's website, 3D Labs website seems to have died in a fire. It is now showing 503 service unavailable, so who knows if it'll ever come back, and if it does come back, who knows what will be on there. I probably should have downloaded all of everything when I had the opportunity. Something inside me said that I should, and I didn't listen. Anyway, that was a huge pile of data. I'm going to make the raw spreadsheet available as a Google Sheet. The link will be down below in the description. Some of this hardware will come back again later for some future videos. Some of it, maybe not. In the meantime, remember to like and subscribe. Follow me on Twitter and Instagram. I usually post pictures of things that are going to appear, possibly going to appear in future videos, and otherwise just, you know, weird old stuff. So until next time, try to remember the good stuff.